Hello students, welcome to all. In this lecture we discuss the new article Statistical Mechanics. Now what is statistical mechanics? That we firstly note here. It is a branch of physics which deals with statistical treatments of macroscopic system. Now what is a macroscopic system? That macroscopic system which consists of very large number of microsystem. That is, we just take one example, gas system. Hence gas system is a macroscopic system, and that gas system which consists of very large number of micro system, that is number of atoms, molecules and ions. These are in the order of 10 raised to 23 or more. When statistical methods are applied to the macroscopic system, which statistical methods like collection of data, classification of the numerical data as well as its tabulation, such a methods once applied to macroscopic system, then the statistical predictions are nearly correct. It means it not only gives the information of the actual behavior of the system, but that of greatest possibility. Hence, the predictions made by such a methods are nearly correct for the macroscopic system. Then we see classical statistic. Now, what is classical statistic? That statistic was developed by Maxwell, Boltzmann, Boltzmann and Gibbs. Therefore, the statistic we call here classical Maxwell-Boltzmann statistic. But how it arises? Since before developing quantum theory, Maxwell and Boltzmann applied the statistical methods to macroscopic system by using classical physics. Therefore, that statistical methods known as classical statistic. That classical statistic is Maxwell-Boltzmann statistic. Such a statistic is applicable to all identical particles. or we say molecules. They must have any spin. Now, these are the characteristics of the Maxwell-Boltzmann statistic. They have any spin as well as all particles are distinguishable. That means individual particle can be easily tracked. Such a statistic which come under the classical statistic. Maxwell-Boltzmann statistic can easily explain the observed physical phenomena like temperature, pressure, energy, etc. But it unable to explain the experimentally observed phenomena, just like black body radiation, specific heat at low temperature, etc. These phenomena are not explained under classical statistics. Therefore, they are explained by using new quantum idea, by using the concept of discrete exchange of energy between the system. The resulting statistic we call quantum statistic. That statistics developed by Bose, Einstein, Fermi, Dirac. Therefore, the two statistics we mentioning here under the quantum statistic, Bose-Einstein statistic, and other one is Fermi-Dirac statistic. Quantum statistics which holds good for photons and elementary particle. Here in that article we discuss about the classical statistic, that is the Maxwell-Boltzmann statistic. Here we consider the all particles are distinguishable, means individual particle can be easily tracked under that statistic. For explaining that concepts, everyone must know the next concept, that is about the phase space. Now, what is phase space? That we explain here. It is the space where all possible states, of the macroscopic system are represented. That means it describes the behavior of dynamical system. For explaining the phase space, here we take example of non-interacting monoatomic gas. System. Under that monoatomic gas system, we specify state of gas for individual particle, individual molecule. Now, how to specify the state of gas for individual molecule or the particle, that we are explaining here. To specify the state of gas, we must require what is its position and velocity. The velocity we express in terms of momentum. Hence, to specify the state of gas, it requires the position coordinate x, y, z. Means x, y, z, it gives position coordinates in a given here the system. As well as it also requires the momentum coordinates, component of the momentum px, py, pz. It gives components momentum in momentum space. Such a position coordinates and momentum coordinates together, it gives one set, and that set is x, y, z, px, py, pz. Such a set which specify state of gas molecule. Hence, to specify state of gas molecule, it requires 6 coordinates. Hence, the space in which to specify the state of gas completely, it requires 6 coordinates. That space we call phase space, or it is also known as 6 dimensional space. In 6 dimensional space, we call it is a phase space. Now, the next point is that in the phase space, we are considering the smallest region which has minimum volume. That smallest region we call is a cell which has minimum volume. Now, how much volume of that cell in the phase space, that we calculating here. Now, we firstly find a small volume element, small volume element in the phase space is denoted by D2. Volume elements which we are considering volume element in related to the position coordinate dx, dy, dz, and corresponding momentum volume of an element in the momentum space, that is dpx, dpy, and dpz. That small volume element in the phase space is for a cell, and that is D2. It is dx, dy, dz, dpx, dpy, dpz. Here What are the dx, dy, dz? These differentials are very small as compared to dimensions of the system, and dpx, dpy, dpz are also small as compared to dimension of the range of the momentum of the molecule, and therefore dx, dy, dz, dpx, dpy, dpz, it is the volume of a cell. That volume of cell has minimum volume that we calculate by using according to the Heisenberg's uncertainty principle. Now, what is the Heisenberg's uncertainty principle? It is impossible to measure position and momentum coordinate simultaneously with an arbitrary accuracy. That means delta x, delta px is always greater than or equal to h or h cross. Similarly, delta py into delta y is always greater than equal to h or h cross, and also along the z axis delta z, delta pz greater than equal to h or h cross. Therefore, volume of element, that is a cell, that is d tau is equal to h dx dpx, dy dpy and dz dpz, that equal to h into h into h equal to h cube, or we write in terms of h cross cube. Hence, each cell in a phase space has minimum volume of the order of h cube. Hence, remembering here, every point in the cell is not a single point, but the particle can be found somewhere within this small region centered at that point. Now, we find the next point. What is the phase density? Phase density. Phase density denoted by the symbol rho. Phase density is defined as the number of phase points, per unit volume of phase space. Here, the state of gas at any instant of the time is completely specified by phase density, with which the phase points are distributed in a given phase space. Here, if all states in the given system are related to the probability, all states in the given systems are related to probability. Then what is the sum of probability of all possible states? that we find here, sum of probabilities of all possible states of the system is always unity. That means the integral of rho d tau is always equal to 1. Here we note here, in statistical equilibrium, the density of the phase points phase density in the phase space is independent of time at all points in phase space. Hence, remember, in that lecture we explain the various terms like the classical statistic, that statistic known as Maxwell-Boltzmann statistic, and it is applicable to all identical particles or the molecules, they having any spin and distinguishable. Example, we get here the gas molecule, and it satisfactorily explain some observed physical phenomena like temperature, pressure, energy, but that statistic was unable to explain the various experimentally observed phenomena like black body radiation as well as specific heat of gas at low temperature. Therefore, these experimental phenomena were explained by using new quantum idea. In that idea, we consider the discrete energy exchange of energy between the system. The resulting statistic known as quantum statistic. That quantum statistic is of the two types, Bose-Einstein statistic and Fermi-Dirac statistic. Example, or that statistic holds good for photons and elementary particle. And then we explain what about the phase space. Phase space is a 6-dimensional space, that in that space we specify all possible states of gas of a microscopic system. To specify the state of gas, firstly we mention it require position and velocity. Hence, we consider the position coordinates and momentum coordinates in the momentum space. These two coordinates together gives a one set. That set define the state of gas molecule. Hence, phase space is a 6-dimensional space that we define. Here in the phase space, we choose the smallest region which has very small volume or the minimum volume. That region we call cell. Hence, what is the volume of a cell in the phase space that denoted by d2, and it is the product of differentials of dx dy dz, which are very small as compared to dimension of the system, and differential dpx dpy dpz are also small as compared to the limit of the momentum space. The product of the two terms gives small volume element. That small volume element, we find its value by using Heisenberg's uncertainty principle. It gives d2 equal to h cube or h cross cube. Hence, each cell in the phase space denoted by has small minimum value h cube or h cross cube. Then we find phase density, the number of phase points per unit volume of the phase space. If all states in the system which are related to the probability, then we find the sum of probabilities of all possible states of a macroscopic system remains unit, that is integration of rho d2 equal to 1. If the system is in statistical equilibrium, then the phase density is independent of time at all points in the phase space, and that is the result of that article. Thank you.